Hello, my name is Hans Burgerhoff and I work as a statistician in the UNCG. This video is part of a series of videos about medical statistics. In this video, I will tell you about statistical tests for normally distributed variables. I will start with a recap of a statistical test and tell you how to check whether data are normally distributed. Next, I will show you an example of a one-sample t-test, followed by a t-test for two independent groups. The last part of this video will be about the one-way Anova, a way of comparing means of three or more independent groups and how to deal with multiple comparisons. Like in other videos, I will use data from the article about IVF offspring to illustrate the statistical tests. In this case, we will have a look at the birth weights of the children. For the tests in this video, t-tests and Anova, we assume that the distributions of the outcome variable in all groups are normal distributions. How to check if the data are normally distributed? Official statistical tests for normality exist, but they are not always that useful. If the sample size n is small, they have low power. If n is large, the assumption of normality of the distribution itself is of less importance because of the central limit theorem. The sample distribution of the mean will be normal for large n. We will have a look at the specific graph in order to inspect the observed data visually, the QQ plot. Please note this is called inverse normal in Kirkwood and Stern. Here we see a histogram of the birth weights of the children. Also in the graph, a normal distribution is shown, with the same mean and standard deviation as the observed data. Can we say that the birth weights are normally distributed? In some situations it can be hard comparing bars of a histogram to a smooth normal curve. A QQ plot can be helpful. For this, we take a quantile Q from the empirical distribution. There is a certain percentage of the observations, let's say x, on the left-hand side of the blue Q. We will calculate the corresponding quantile in the normal distribution, the red Q. Now, if the observed distribution is close to the normal distribution, the blue and red Q will be almost the same value for all possible choices of the blue Q. The blue and red Qs are plotted in the so-called QQ plot. If the blue and red Qs are almost the same, the points in the graph will be close to the line y equals x. In some situations, it's easier to judge if points are on a straight line than comparing bars to curves. So a QQ plot can be useful for checking normality. To refresh your memory about statistical testing, what's it all about? We have a research hypothesis. Based on our experience, we might think that the mean birth weight of IVF offspring is lower than the mean of a certain reference population. Let us assume that the mean of this other population is known to be 3,500 grams. We will translate this in a null hypothesis and an alternative hypothesis. The H0 states mu equals 3,500. The alternative states mu smaller than 3,500. To keep things simple, we will start with the unrealistic situation that the standard deviation of the birth weights in the population of the IVF offspring is known. In this case, sigma equals 500 grams. We will test the null hypothesis mu equals 3,500 against the alternative mu is smaller than 3,500 grams. We have a sample of 115 children, all born after IVF, and the sample mean equals 3,393.3 grams. To perform a test, we have to standardize it. We standardize the sample mean by subtracting the hypothesized mean, 3,500, and dividing by the standard error. The standard error is sigma divided by the square root of n. Because sigma is known, we can transform this to a z value. So we can divide the difference, minus 106.7, by the standard error 46.6. This will lead to a z value of minus 2.29. From the table of the standard normal distribution, we can find the p-value equal to 0.011. This p-value is smaller than alpha, if alpha is 0.05, so we will reject the null hypothesis. The conclusion will be that children born after IVF have on average significantly lower birth weights than the children from the reference population. Now we go to the more realistic situation in which the population standard deviation sigma is not known, and we will have to estimate this unknown population standard deviation by using the sample information. We will test the very same null hypothesis against the same alternative, mu smaller than 3,500 grams. Again, we have to standardize the information from the sample. The sample mean was 3,393.3, but now we have to use the sample standard deviation because sigma is unknown. Standardization will be to the t-value now, because there is more uncertainty. The difference of minus 106.7 will be divided by s divided by the square root of n, which is 53.3. This will lead to the probability that t is smaller than minus 2.00. This is almost 0.025, and that's what we found in the table of the t-distribution I will show you on the next slide. Here we see the table of the t-distribution from the book of Kirkwood and Stern. We had a one-sample problem with 115 observations, so the degrees of freedom, n-1, equals 114. From the sample, we calculated a t-value of minus 2. We were interested in the probability of finding this t-value, or even smaller, if the null hypothesis is true. The table in the book only gives positive reference values for several t-distributions depending on the degrees of freedom. Now remember, a t-distribution is a symmetric distribution with mean 0. So the area on the left-hand side of minus 2 is equal to the area on the right-hand side of the value 2. In the table, there is no entry for 114 degrees of freedom. The closest is 120 degrees of freedom, and we will use this as an approximation. Moving to the right in the table, we observe critical value 1.98, which is close to our observed value of 2. The area in the right-hand side tail is 0.025. So the p-value we are looking for is close to the value 0.025. In SPSS, it's possible to calculate the p-value more exactly by using the standard function CDFT, the cumulative distribution function of the t-distribution. We have to fill in the t-value we are interested in, minus 2, and the number of degrees of freedom, 114. And SPSS will calculate for us, with a lot of decimal places, the p-value. In this case, it's rounded 0.024, which is close to the table value 0.025. 0.025. So we can fill in the 0.024. The p-value is smaller than alpha, so again we will reject the null hypothesis. The conclusion of the t-test would be that children born after IVF have, on average, significantly lower birth weight than the children from the reference population. We calculated the one-sample t-test by hand. It's also possible to have SPSS do the calculations. In the menu, choose Analyze, Compare Means, One-Sample t-test. In the dialog window, fill in the outcome variable, birth weight, and the value 3,500. SPSS will give a table with descriptives in the output file and the results of the one-sample t-test. By default, SPSS will give the two-sided p-value, which is twice the one-sided p-value we calculated by hand. In a lot of situations, we would like to compare two independent groups with respect to the means of a normally distributed variable. The null hypothesis will generally state μ1 equals μ2. For example, we have a population of children born after IVF. Both population mean and standard deviation are unknown. We have a second population, naturally conceived children from subfertile mothers, from which also mean and standard deviation are unknown. We will take a random sample from the first population and calculate sample mean and sample standard deviation. And we will do the very same for the other population. If we want to test the null hypothesis of equal means, we have to know the standard error of the difference in means. And for that, we need the standard deviations. If we may assume that the populations have the same variance, it's most efficient to use all information of both samples to have one estimate of the common variance. We call this a pooled estimate. If both samples are equal in size, we will estimate the pooled variance as the mean of the variances. So the pooled standard deviation will be the square root of it. If the sample size are not equal, however, the largest group will probably have the most precise estimate. We will use the degrees of freedom of each sample as a weighting factor. Here you see the formula for the pooled variance. It's calculated by taking the variance of the first sample, multiply it by n1 minus 1, taking the variance of the second sample, multiplied by n2 minus 1, sum them up, and divide by the total sum of the weighting factors, n1 plus n2 minus 2. This is the formula for the pooled variance, so the pooled standard deviation is the square root of it. How do we know if the variances in the groups are equal? Several statistical tests exist for testing the homogeneity of variances. SPSS uses Levene's test to test the null hypothesis of equal variances. Sigma 1 squared equals sigma 2 squared. If the p-value of Levene's test is smaller than or equal to 0.05, we are not allowed to pool the variances. Some statisticians are more stringent and take an alpha of 0.25 for this test. What if we cannot assume that the variances in the groups are equal? Well, then we have to estimate the standard deviation for each group separately. The standard error for the difference in means can be calculated by taking the standard error of the first group squared plus the standard error of the second group squared and take the square root of it. If we can assume equal variances, then we will have a pooled estimate and just plug in the pooled estimate in the formula above. Fill in the SP for both S1 and S2, and you will get one pooled standard error. We saw a lot of formulas. Let's see what SPSS can do for us. We would like to test the null hypothesis that the mean birth weights of the two samples are equal. Based on the histograms of both groups, we decide that the distributions are almost normal. To perform the t-test for independent groups in SPSS, we choose in the menu Analyze, Compare Means, and Independent Samples t-test. In the dialog window, we fill in the outcome variable, birth weight, and the grouping variable, in this case group IVF, and its codes. In this case 0 and 1 were used. SPSS will give the output in the output file. First of all, we see a table with descriptive information. We see the number in the groups, the mean birth weights for each group, the standard deviations, and also the standard errors. Remember, the standard error was defined as the standard deviation divided by the square root of n. Next, we see a large table with a lot of information. First of all, we see a mean difference. The mean difference is simply the difference between the means. So we observe a difference of 184 grams between the two group means, the two sample means. Is it significant or not? We will have to test it with the t-test. But we observe two t-tests. There is a t-test with equal variances assumed, and there is also a t-test with equal variances not assumed. Each t-test has its own estimate of the standard error of the difference in means. It's 80.5 for the equal variances assumed t-test and 79 for the other t-test. Both t-tests have their own t-value. The t-value is calculated by taking the mean difference, 184.6 for example, divided by the standard error. It will lead to a t-value of 2.29 for the t-test assuming equal variances. For the other t-test, 184 divided by 79 will give a value of 2.33. How do we know which of the t-tests we have to use? Well, we can see it from Levene's test of equality of variances. In this case, the p-value of Levene's test is 0.3, which is larger than alpha, so we cannot reject the null hypothesis, and we can assume they are equal, because the null hypothesis states variance in group 1 equals the variance in group 2. This is not rejected, so we can assume they are equal. If they are equal, we can use the equal variances assumed t-test. The p-value of this test is 0.023. It is smaller than alpha, so we will reject the null hypothesis. The null hypothesis of equal means will be rejected. So the conclusion will be, based on the information in the descriptives, that the mean birth weight in the group of IVF offspring is significantly lower than the other group. Now we go to the problem that we have more than two groups, and we want to compare them with respect to a continuous outcome variable. For this, I use another dataset. It's a so-called built-in dataset of SPSS, containing information about over 1,200 women with breast cancer. We have 3 groups based on the histologic grade of the tumor, which is a measure of aggressiveness of the tumor, and our outcome variable is the tumor size. How to compare means of more than 2 groups? If we have more than 2 groups, we have the problem of multiple testing. If we would perform all pairwise comparisons, with alpha is 0.05 for each test, the overall alpha will be larger than 0.05. The overall alpha is the probability of rejecting at least one null hypothesis falsely. Possible solutions for the problem of multiple testing is to perform an overall test first, and in case of a significant overall test, performing post hoc tests, keeping the total alpha under control, or we can perform all pairwise tests, each with a smaller alpha. The Bonferroni procedure is an example of this solution. First, we will have a look at the one-way Anova, the overall test. The null hypothesis states that all means are equal. The alternative says at least 2 of the means are not equal. The overall test is the one-way Anova, Anova being short for analysis of variance. The assumptions for a one-way Anova: we should have independent observations, the distribution should be normal for each group, and equal variances for all groups. In fact, these are the same assumptions as for the pooled t-test. Here we see histograms of tumor sizes for the 3 groups. The higher the score on histologic grade, the more aggressive the tumor. We see rather skewed distributions, and for data like this it can be useful to use a transformation before analyzing the data. If we perform a logarithmic transformation, the distributions look more normal, and also the variances in the groups seem to be more equal. So we will analyze the data on the log scale. To perform a one-way Anova in SPSS, you have to choose Analyze, Compare Means, and One-Way Anova in the menu. You will get this dialog window, in which you have to put in the dependent variable, in this case the logarithm of the tumor size. You have to tell SPSS what is the grouping factor, in this case histologic grade, and you can choose for options. I would advise to choose descriptives and homogeneity of variance test. This is the first part of the output. We see descriptives for each group. The outcome variable is the size of the tumor on the log scale. We see means for the different groups and also standard deviations for the groups. Our research question is whether the means are equal. An assumption for the Anova is equal variances. So we would like to test the null hypothesis variance 1 equals variance 2 equals variance 3. SPSS has a test for this, the homogeneity of variances test. It's Levene's test like it is in the independent sample t-test. In this case, the p-value is 0.86, larger than 0.05, so we will not reject the null hypothesis of equal variances. So we can perform the Anova. This is the Anova table. Anova was short for analysis of variance. But what's exactly going on in the table? And what conclusion can be drawn? Well, to understand what's going on, it's important to realize that the definition of variance was given by the sum of all squared deviations divided by n-1. A sum of squares. It has something to do with the first column. In the figure, we see the logarithm of the tumor size plotted against the histologic grade. The red crosses are the group means, and the horizontal line depicts the overall mean. The total sum of the square deviations will be split into two parts: the sum of squares between the groups and the sum of squares within the group. In the Anova table, we see that the total sum of squares equals 313.76. This is split in a sum of squares equal to 22.87 between the groups and 219.89 within the groups. If we divide a sum of squares by the corresponding degrees of freedom, we get the column mean square. If the null hypothesis is true, both mean squares are estimates for the very same variance. The ratio between the two mean squares is calculated and given in the column with heading F. 11.4 divided by 0.33 is almost 34. If the null hypothesis is true, we expect the mean squares to be equal, so we expect a ratio of 1. The probability of finding a ratio of 34 or even more is smaller than 0.001, so we can reject the null hypothesis of equal means. But we still do not know between which groups significant differences exist. That's why we look at so-called post hoc tests, also called multiple comparisons. We will make pairwise comparisons of the groups while taking the overall alpha into account. There are many options to perform post hoc tests. There are many different tests, each optimal under certain circumstances. I will just show you the least significant difference, the LSD, after an Anova, and we will have a look at the Bonferroni procedure. This is in fact a one-step procedure. There is no Anova needed. It's a simple method, but conservative if many groups are involved. The idea is quite simple. If you are going to perform CT tests, and you want an overall alpha of 0.05, then use for each test the 0.05 divided by the number of tests you're going to perform. This is the first example of the post hoc test, the LSD. According to the LSD method, all pairwise comparisons have been calculated. 1 with 2, 1 with 3, and 2 with 3. In fact, SPSS shows 6 tests, but the comparison of group 1 with 2 is equal to the comparison of group 2 with 1. All tests are performed using a common standard deviation based on all groups. The p-values are all very small, all smaller than 0.001. In the case of 3 groups, we can compare these p-values to alpha of 0.05, and we will conclude that all groups have significantly different means. If you double-click on the table in SPSS output and again double-click on a number, you will get more details. This p-value, for example, is around 6.2 times 10 to the power minus 7. So indeed, very, very small. Here we see a similar table according to the Bonferroni procedure. This is a one-step procedure. There is no need doing the Anova first, and we can compare the groups directly. Like the LSD procedure, all pairwise comparisons are performed with a common standard deviation based on all groups. To keep the overall alpha small, each test is performed with a smaller alpha equal to the overall alpha divided by the number of tests, in this case 3. As a service, SPSS already multiplied the p-values by 3. We call this the Bonferroni corrected p-value, and we can simply compare these p-values with 0.05. Again, with double-clicking on a value, we can see that the p-value of this test was 2 times 10 to the power minus 6. And indeed, this is almost 3 times the p-value we observed before. To conclude, both the Anova followed by LSD as the Bonferroni procedure will conclude there are significant differences between all groups. The higher the histolic grade, the larger the mean of the log of the tumor sizes. From that we can conclude that there is a significant difference in geometric means on the original scale. If you want to know more about post hoc tests, you can find information on the internet, for example by using these links. Well, that's it for testing normally distributed variables. I hope it was clear. Please make the exercises and check your answers. See you in another video.